Okay guys, welcome to the first video in Outcome R10 right over there. Take a look. See, it's written right there. Outcome R10, we're going to deal with geometric sequences and series. Let's get started right now. Okay, so welcome to lesson 1.3. And we'll start off by considering this sequence right here that I'm circling. 1, 2, 4, 8, and 16. Now there is a pattern to this sequence, but it's different than the arithmetic ones we've seen before. We can see that the difference between terms is not constant. Okay, that's very important for us, that the difference is not constant. And that matters a lot. Therefore, we can say that this is not arithmetic. It's not arithmetic. That's too bad. But there is a pattern, so we want to talk about that pattern. There is something that relates successive terms. In fact, there's something called a common ratio. Common ratio between consecutive terms. Aha! And that common ratio seems to remain constant. In fact, we'll write R for the common ratio. If we look at term 2 divided by term 1, it's 2 divided by 1, and that gives us 2. If we look at finding R by taking term 3 divided by term 2, that's also 2. If we wanted to calculate R by taking, say, term 5, 16, divided by term 4, 8, we also get 2, and so on and so forth. So what are we finding here? Is that each term is the previous term times 2. Okay, so we can define this idea here. And we say that this is a geometric sequence. Okay? A geometric sequence is a sequence with, well, you guessed it, a common ratio. And that common ratio is denoted as R between consecutive terms. Now, we can use geometric sequences for lots of things. So, geometric sequences are useful for making predictions about quantities that grow and decay exponentially, such as populations, bacteria, compound interest, uranium, and much, much, much more. It's surprising how many different applications there are. Okay, so let's take a look at this example here. And I want you to try and answer this one just based on what you know about different sequences, like arithmetic and geometric, and see what category these things fall into. So this example says, are these sequences arithmetic, geometric, or neither? And if they are a sequence, what is the common difference or ratio? So if they're arithmetic, what's the common difference? And if it's geometric, what's the common ratio? I'm going to pause the video now and you try to answer for all 6 questions below. Okay, hopefully you've had a chance to guess now. So I've shifted up to look at these 6. Here we go. The ones that are arithmetic will grow by the same amount. Question A is arithmetic. Okay, it is actually going up by a common difference. How much is it going up by? It's going up by 21. So you add 21 to negative 8, you get 13, and add another 21, you get 34. Okay, so that one we could say is an arithmetic sequence. Okay, for none of the other ones do we have an arithmetic. This is the only arithmetic sequence. Okay, now what about the other ones? Well, let's see. Question B, this one's geometric. Okay, it's geometric. And so for the geometric sequence, we have to check to see is each term being multiplied by the same common ratio. In fact, it is. If you take 15 divided by negative 3, 15 over negative 3, you get negative 5. And in fact, if you take 15 times negative 5, you'll get negative 75. And times negative 5, well, you get positive 375, and so on and so forth. This is a geometric sequence with a common ratio of negative 5. Okay, let's see. What else is geometric here? Oh, D is also geometric. D is geometric. It might be surprising that it's geometric, but just take a look at it. What would I multiply 1/2 by to get 1/6? Well, a little bit of fancy footwork and you'll discover that's actually a third. Okay? And in fact, if I multiply 1/6 by a third, I get 1/18th, and by another third, I get 1/54th, etc., etc. And so in fact, I could say that 1/3 is my common ratio. And this is again a geometric sequence. Are there other geometric sequences here? Well, you might be surprised to discover that E is geometric. How can that be? Well, what am I multiplying by to get from term 1 to term 2? Well, let's see. The ratio between term 1 and term 2, take term 2 divided by term 1, gets me -1. And in fact, if you look carefully at this sequence, I'm multiplying by -1 every time. 2 times -1 gives me -2. Times -1 gives me +2. Times -1 gives me -2, and so on and so forth. So in fact, this is a geometric sequence. Is there another one? Yeah, there's one more. F is a geometric sequence. I'm multiplying every term by B to get the next term. In fact, the next term in the sequence, if you thought about it, would be AB cubed. And then AB to the power of 4, and then AB to the power of 5, and so on and so forth. The common ratio is B. So all these ones that I've circled in red are geometric. Our last one, though, over here, is neither. It is neither arithmetic nor geometric. It doesn't have a common difference, so it's not arithmetic. And it doesn't have a common ratio, so it's not geometric. And you may recognize this. These are a series of perfect cubes. Anyway, let's continue on. To find any term Tn in a geometric sequence, we can use the general term, also known as the nth term. How do we find the nth term? Well, we start with term 1, and we multiply term 1 by a common ratio. And then we multiply it by a common ratio again, and again, and again. Over and over again. How many common ratios do we need to multiply by to get the nth term? N minus 1 common ratios. Think about it. To get the third term, you take the first term and you multiply by the common ratio twice. To get the fifth term, you take the first term and you multiply it by the common ratio 4 times. You will have n minus 1 common ratios between T1 and Tn. Okay, so let's fill in the blanks over here. Okay. Tn is the value of the nth term. T1 is the value of the first term. R, well, again, this is our common ratio. And N is the term number. Okay, let's scan down and take a look at the next example. Given the sequence 2, 4, 8, 16, I want to find the nth term and the 10th term. Okay, so the nth term can be given by the formula Tn equals T1 times R to the power of n minus 1. So T1 is over here. That's 2. And what's R? Well, a quick calculation will tell me that R is 4 divided by 2, which is 2. Or we could have said r is 8 divided by 4, or 16 divided by 8. And what we're saying is that we take the first term and multiply it by 2 to get the next term, and multiply by 2 to get the next term, and so on. So in general, if you wanted to find the nth term, you take t1, which is 2, times the common ratio 2 to the power of n minus 1. We could actually simplify this expression, and we get t1 equals 2 to the power of n. That is the nth term. Now, if we wanted to, in part B, find the 10th term, we just simply substitute for 10 in our formula, and we get that the 10th term is 2 to the power of 10. That's a really big number. That's in fact 1024. Notice with geometric sequences, if r is greater than 1, you'll actually end up with really large terms very quickly. Okay, in the final page of this section, there are 2 more questions dealing with the previous sequence. I'd like you to pause the video now and try them, and I'll have the solutions in one moment. Okay, welcome back. For this one here, the 21st term, we just simply plug the formula that we established before. T21 is 2 to the power of 21, and that's 2,097,152. What about D? Well, D, we've said that the term value is 4,096, and we're asking what is the n? What number of term is this? Well, right now in grade 11, you don't actually have a method for solving this other than guessing and checking. And in fact, if you guessed n equals 12, you're right. 2 to the power of 12 happens to be 4,096. In grade 12, we'll develop a much better, cleaner method for finding that value. Our next example deals with bacterial population. I'd like you to take a moment to read this and attempt to think of a way of solving this problem. I'm going to pause the video now and write some things down, so I suggest you pause as well. Okay, here I've started the problem. I said that we've got a sequence 5, 10, 20, 40, etc. I said, well, what would be the general term, or the nth term of the sequence? Well, the first term is 5, and the common ratio is 2. So we have a formula Tn equals 5 times 2 to the power of n minus 1. Now we have to be careful here, and I made a little note. N is the number of the sequence, and so it's the number of half days that have passed. Remember, this is doubling every 12 hours. So n is the number of half days. If we want to write a formula in terms of the number of days that have passed, okay, the number of days that have passed is going to be given by this. 5 times 2 to the power of n over 2 minus 1. Okay, if n were the number of days, then n divided by 2 is the number of half days. So we could write this where n is the number of days. Either formula here or here is acceptable. What's important for us is that we understand that one of these formula is referring to the number of half days, whereas the other formula refers to the number of days. Okay, finally we have a final example here, which for some reason is numbered example number 7 on this sheet. Oh well. Anyway, let's see. The second term of a geometric sequence is 28, and term 5 is 1,792. Find the generating function for this sequence. Well, what I'm going to do is draw it out. Term 1 I don't know. Term 2 is 28. Term 3 I don't know. Term 4 I don't know. Term 5 is 1792, etc. Well, now just think about it. How did I get from term 2 to term 3? Well, I multiply by r. To get from term 3 to term 4, I multiply by r. From term 4 to term 5, hey, I multiply by r. In other words, if I take 28 and multiply it by r 3 times, I get 1792. Isolating r cubed, we get 1792 divided by 28. Type that into my calculator, and I get 64. So r is equal to the cube root of 64, which is actually plus or minus 4. Now, which is it? What do you think? Well, actually, it's not plus or minus 4. That's a mistake. We tend to make that mistake when we're thinking about square roots. But for the cube root, it must be plus 4. Because if I had negative 4 times itself 2 times over, I would actually get negative 64. So in fact, it's positive 4 for r. And so now I can write out the generating function. This is another way of saying Tn. Is term 1. Hey, what's term 1? Times r to the power of n minus 1. Well, if r is 4, going backwards, dividing by 4, I find 7 for the first term. And so I have this as the generating function. Okay, here listed is the homework for this section. Enjoy! See you in class.